Hello everyone, I'm academician Dr. Lilia. Welcome to Science and Me YouTube channel. The mission of my channel is to introduce you to popular science and to create a popular science encyclopedia on YouTube. We are back with an interesting popular science video. I would be very happy if you support me by subscribing to my channel and writing a comment. If you are ready, let's start the video. Chaos theory is a branch of mathematics and science that deals with the behavior of dynamical systems that are highly sensitive to initial conditions. It seeks to understand and describe seemingly random or unpredictable behavior in deterministic systems. This means that small changes in the initial state of the system can lead to large and unpredictable changes in its future behavior. Chaos theory has applications in various fields, including physics, biology, economics, and engineering. Here are some key mathematical concepts and principles associated with chaos theory. Nonlinear dynamics. Chaos theory primarily deals with nonlinear dynamical systems, where the relationships between variables are not proportional. Nonlinearity is a fundamental aspect of chaotic behavior. Nonlinear dynamics is the study of dynamical systems that are not linear. Chaotic systems are typically nonlinear. Chaos theory is a complex and rapidly developing field of mathematics. However, it has already had a major impact on our understanding of the world around us. Deterministic chaos. Chaotic systems are deterministic, meaning that their future behavior is entirely determined by their initial conditions and the system's governing equations. However, small changes in the initial conditions can lead to vastly different outcomes, making long-term predictions impossible. Phase space. In chaos theory, systems are often represented in phase space, which is a multi-dimensional space where each dimension corresponds to a variable describing the system. Trajectories in phase space represent the system's evolution over time. Strange attractors. Chaotic systems often exhibit strange attractors, which are complex, self-replicating patterns within the system's phase space. These attractors are a characteristic feature of chaos and help describe the long-term behavior of the system. Sensitivity to initial conditions. The butterfly effect. A defining feature of chaos is the butterfly effect, which states that small changes in initial conditions can lead to significantly different outcomes. This sensitivity to initial conditions is quantified by the Lyapunov exponent, which measures the rate at which nearby trajectories diverge. Bifurcations. Bifurcations occur when the parameters of a dynamical system are changed, leading to a qualitative change in the system's behavior. Period doubling bifurcations are a common occurrence in chaotic systems. Periodic orbits and chaos. Chaotic systems can contain both periodic and chaotic orbits. Periodic orbits represent regular, repeating behavior, while chaotic orbits are aperiodic and unpredictable. Feigenbaum constants. The Feigenbaum constants, alpha and delta, describe the scaling behavior of bifurcation intervals as a system approaches chaos through period doubling bifurcations. These constants have universal values that apply to many different chaotic systems. Fractals. Fractal geometry is often associated with chaos theory. Fractals are self-replicating geometric patterns that can be used to describe the irregular and self-similar structures found in chaotic systems. Fractals are geometric objects that have a self-similar structure at all scales. They are often used to model chaotic systems. Lorentz system. The Lorentz system is a famous example of a simple set of nonlinear differential equations that exhibit chaotic behavior. It was developed by meteorologist Edward Lorenz and is often referred to as the Lorenz attractor. Mandelbrot set. The Mandelbrot set is a famous fractal that arises from the iterative application of a simple mathematical formula. It is a visually striking example of self-similarity and complexity in mathematics. Chaos theory has profound implications for our understanding of complex systems and has led to advancements in various fields, including weather prediction, cryptography, and the study of biological systems. It has also had an impact on philosophy and our understanding of determinism and predictability in nature. One of the key mathematical concepts in chaos theory is the butterfly effect. This is the idea that a small change in one part of a system can have a large and unpredictable effect on another part of the system, even if the two parts are very far apart. The butterfly effect can be illustrated by the following example. Suppose we have a weather system that is described by a set of differential equations. If we solve these equations for two different initial conditions that are very close together, the resulting solutions will also be very close together at first. However, as the solutions evolve over time, they will diverge more and more, and eventually become completely different. This is because the weather system is highly sensitive to initial conditions. Even a small change in the initial state of the system, such as the flapping of a butterfly's wings, can lead to a large and unpredictable change in its future behavior. Chaos theory has a wide range of applications in science and engineering. For example, it is used to study the weather, climate change, the stock market, and the spread of diseases. Here are some examples of mathematical tools and techniques that are used in chaos theory. Differential equations. Differential equations are used to describe the evolution of a dynamical system over time. Lyapunov exponents. Lyapunov exponents are used to measure the sensitivity of a dynamical system to initial conditions. Applications of the mathematics of chaos theory. The mathematics of chaos theory is used in a wide range of fields, including meteorology. Chaos theory is used to study the weather and climate. For example, it is used to develop weather forecasting models and to predict the long-term effects of climate change. Economics. Chaos theory is used to study the stock market and other economic systems. For example, it is used to develop trading strategies and to predict financial crises. Biology. Chaos theory is used to study the spread of diseases and the dynamics of populations. For example, it is used to develop models for the spread of the COVID-19 pandemic. Engineering. Chaos theory is used to design and control complex systems, such as aircraft and power grids. For example, it is used to develop flight control systems and to prevent blackouts. Chaos theory is a powerful tool that can be used to study and understand a wide range of complex systems. Dear friend, I hope you benefited from the video. Thank you for watching today's video. If you enjoy content like this, please don't forget to subscribe to my channel and click on the notification bell to stay updated with new videos. Also, if you liked it, be sure to leave a like and share your thoughts in the comments. Looking forward to seeing you again with new videos. I can't wait to bring you more knowledge from the enchanting world of science.